All right, let's begin. I think that's those things. Yep. Okay. All right. So let's see what we should talk about in terms of announcements. So I guess, uh-oh, hopefully this doesn't screw it up. Okay. Hopefully, so on the last quiz, I guess we're just going to like drop question 2. Or maybe I'll just give everyone like points for it, so I guess like plus whatever, I think it's like plus 3 points. Yeah. So you can get some extra credit on it, maybe. Yeah. So, and then I will release exam 1 today. Exam 1 today, and it will be due this this Friday. And then, what else should I say? Homework. I guess I'll release homework 3. I'll release that on Wednesday, and it'll be due the next Wednesday. Or maybe I can make this due this upcoming next Monday. So next Monday. And then this will be due next Wednesday. Okay. I think that's it for those kinds of things. I had a thought, and I don't know how smart or stupid it is. I had an idea, and this was the idea. We would have, we would replace, or kind of maybe replace one quiz. Yeah, exam 1 will only cover the material from last week and the week before, so weeks 1 and 2. So we could replace one quiz with a maybe. I guess I could call it something like a with like I'll call it like a an interview quiz or something. The idea is that you would have I would basically give you a question, and what we would do is probably on Discord, we would share a live board and you could solve it. And I guess the feeling that I have is that maybe we could operate it by, I know that you guys probably won't get the reference, but I'm going to say this anyway. Princeton, qual rules, where basically what that means is that, since it'll be in real time, if you guys need a hint or something, hints will be given. The purpose of this is basically to kind of talk to you in person and to actually have a conversation about the material and demonstrate your knowledge and that kind of stuff. So if you don't get the question, if you're not immediately sure how to start or anything, then that would be the way it is. And then I would definitely give hints along the way. And then the other thing that I would say is that in terms of what kind of questions I would give, I think I would give either homework questions or questions that are like the homework problems, except they might just have a number changed or something like that. So basically I'll just put it in quotation marks. So homework questions. So anyway, this is what I'm currently thinking. And this is just because, and so in case you're wondering, is this going to be in front of the class or anything? No, this is going to be like basically just a Discord conversation. So the idea is that you'll sign up for some kind of either an appointment or we'll schedule a time, and then you'll have like 15 minutes kind of thing. Ideally, the question should take about 10 minutes, or less, but I'll probably schedule about 15 minutes per thing. Anyway, if you guys, I'm sure that I have a feeling like most people are not gonna like this idea, at least initially, probably. But maybe if you guys want to give it a try, I think it'd be interesting to at least give this thing kind of a try. Anyway, okay, that's my current feeling on it. Yeah, so the reason why I might want to do something like this is mainly because, most students and I are, during this class are not really able to have any interaction really more than me talking at you, and so this is kind of like a replacement for human interaction, if you want to, perhaps, I don't know. Anyway, okay. Okay, so I think that's all I'm going to say about that for now. I think instead what I'll do is I'll just start with the material. If you guys have any comments, can you look at number 2 on the quiz? The answer is no, I can't, because I have forgotten my cell phone somewhere and Blackboard locked me out. So I need to get access to Blackboard. That's the reason why I didn't fix it, is because I've been locked out from Blackboard until I get my cell phone working again. Okay, so I just want to start on this stuff today. So, I guess someone could copy and paste number 2 in the... for those of you who turned it in, are you going to be able to try it? Probably not. I don't want to go back. What I'll probably do instead of having it just be retried is I'll just add 3 points, right? So you're just going to get 3 points on that question. So, okay. Let me define even and odd. I know I did it in previous classes, but let's just define it here. So, basically, I guess we could almost write this in quantifiers, right? An integer is even when there exists another integer k so that n is equal to 2k. So what does that really mean? So when I say that an integer n is even when there exists a k such that n is equal to 2k. So what I really mean by that is that if you take n and you divide it by 2, you are left with an integer, right? That's the point here. So and then for instance, so like I guess 8, you can say 8 is even because I guess instead of doing that I can just say because there exists the integer 4 such that 8 is equal to 2 times 4, like that. And so that's how we understand what even is. And so if you say, well, 7 is even, because there exists, let's say, some k, so that 7 is equal to 2 times k, then the problem here is that if you divide it by 2, then what you're going to get over here is 3.5. Of course, 3.5 is a rational number and not a... So 3.5 is a rational number, so it's not an integer. So the question is, does this even exist? If we're talking about the integers, then 3.5 doesn't even exist. So that's why 3.5 equals k, but this number is like a DNE because it's not an integer. We'll use a certain rule to prove that it's even or odd. Well, this is the definition, so this is the rule that you would use. Okay. And then, of course, oddness has the same property, right? An integer n is odd when there exists another integer k, so that n is equal to 2k plus 1. And so the only difference between even and odd is this 2k plus 1 business here. So, yes, that's right. So here's the thing, like, is it also the case that an integer, an int, something is odd when, say, z is equal to 2k minus 1. So when, I guess we could say exists k inside the integers such that this is the case. And so remember that the definition of oddness is that there exists a k so that z is equal to 2k plus 1. But my question is it the same thing to say, well, what about the 2k minus 1 case? Like, what does that do for us? And the answer is that it's actually the same. And the reason why is because this k here, there's nothing terribly special about this k except for the fact that it's the thing that makes it even or odd. So for instance here, if we said, 5 is odd because 5 is equal to 2 times 2, where this is our number k plus 1, okay, fine. But isn't it also equal to 2 times 3 minus 1, right? Because this is 6 minus 1, which is 5 again. And you're like, well, yeah, so, so this arithmetic is true. The question is, does it show that the number is odd? And the answer is yes, because, for instance here, if we have an odd number, so let's say that if we have a z which is odd, so then z is equal to 2k plus 1 for some k, then what we can do is we can actually increase k by 1. So we can say z is equal to 2k plus 1. And now keep in mind what we've done if we've increased k by 1 here. If we use k plus 1 here, we're multiplying this by 2 plus 1, but then this is no longer equal to z anymore. This is actually equal to z plus 2. So the only way to fix this is to subtract 2 off of both sides. So we're going to get that z is equal to 2 times k plus 1 minus 1 here. So in this case, let me just call this k prime to differentiate it. So then actually what you would say is that it is true that an integer z is odd when there exists a k prime such that z is equal to 2k prime minus 1. K prime happens to be equal to the original k plus 1, where this is the k that comes from oddness, right? The actual definition. So that, this is a very simple example of something that we can prove. Let's see. Yeah, I'm not sure. Let me check on the stream quality. It looks okay to me, but I guess it's set. I don't know. I think sometimes it'll fix itself. Okay, so are there any questions about this? Honestly, I'm just starting slow today on something I think is relatively easy, so hopefully everybody's kind of more or less on board with this. I'm just kind of talking to myself, so I'm always wondering, if people followed this at all. Okay, so let me try to prove using the... let's prove this fact here. The sum of two odd integers is even. If you subtract 1, you're left with 2k. Yeah, if you subtracted 1 from here, right, you'd be left with 2k. If you subtract 1 inside here where you have to distribute, if you subtract 1 from inside the parentheses, then you actually get a minus 2, right? That's the point here, is that k is equal to, or k prime is equal to k plus 1, but what we're doing is we're multiplying the k plus 1 by 2, and that's why we get this, the error is 2 instead of 1. So let's do another, I'm going to call this another easy fact, and I'm sure that most of you kind of know this, right? If you add up, let's see, let me change this into it. So add two odd numbers, then we get even. Actually, instead of doing any of this, I'm going to just type it, because let's say if x and y are two odd numbers, then x plus y is even. Cool. So if we start with this, then the point here is, and all I tell you is that the numbers are odd. The moral of the story here is that you have to set x to 2k plus 1, and you have to set y as 2j plus 1. So the reason why I'm going through this, and I know that it's actually in the lecture notes, but I'm going through it again just to kind of imply, to say the things that I want to imply. You cannot use y is equal to 2k plus 1 here, right? Because otherwise, if you're doing that, then k here is some fixed number, and so you can't use the same name. So even though the theorem says, or the definition says, that there exists some k, you can change that letter k as long as you make it make sense. So here, we're going to say that there exists some j, such that y is equal to 2j plus 1. Here there exists some k, so that x is equal to 2k plus 1. The reason why we get to do that is because the name doesn't matter. All that matters is that we have this form, this bit of algebra set up. The other thing that's important is that if we use the same letter, then it would actually just imply that x is equal to y. And so it kind of breaks what we're trying to do here. So, okay, cool. So if two numbers are odd, then x plus y is even. So what we get to do here is we can say that x plus y is equal to 2k plus 1 plus 2j plus 1. Which means that we get to rewrite this as 2k plus 2j plus 2, and then what I'm going to do is factor. That's a plus sign. Okay. So, why did I factor out the 2? Well, recall the definition of evenness, right? Recall what it means to be even. What it means is that if I have some number n, which I'm going to set to x plus y, then it's even if there exists a number, in this case it's going to be k plus j plus 1, so that n is equal to 2 times k plus j plus 1 plus nothing, right? That's the definition of evenness. So what this says is once I can pull this 2 out here, this says that this number had to be even. The total number here had to be even. Now k plus j plus 1 could be even or odd, right? We don't know. But what we do know is that 2 times k plus j plus 1 is definitely even. And that's what we were trying to prove. So at this point, we are finished. Any questions about this kind of thing? I mean, I know that this proof itself, right? So I'm not saying that this proof or this fact, right, is complex. I think that this is easy to understand. Normally, I think most of you probably are like, oh yeah, when you add up two numbers that are odd, you're going to get an even number because they each have the, extra 1 in them, and so it should add up. I'm just writing this down so that you have some idea of how the structure of these types of proofs go. So, and then let's do one last one. So we've done this one. And maybe I'll write up the proof for this one too afterward. I just didn't, I wanted to have some space here to write. So for any integer n, n is odd if and only if n squared is odd. So let's look at that as well. So if we'll say something like n is odd, and then I'm just going to write IFF, which means if and only if n squared is odd. So remember what we have to do in this case, right? An if and only if means that first we have to show that if n is odd, then n squared is odd. And then we have to show if n squared is odd, then n is odd. So we have to do both directions because that's what the if and only if tells us to do. So let's look at the first direction. So the first direction here says that if n is odd, then n squared is odd. So remember what the definition of oddness is. It just says that, so I'm going to write this, which means this direction, and I'm going to write that, which means that direction. So this is a fairly common thing you might see in some mathematical textbooks or in notes, where people will just write like, for the direction that goes this way, they'll write an arrow going this way, and then they'll do the proof for that, and then they'll write the arrow going backwards, and then they'll do the proof for that, just to keep things organized. So n is odd means that n is equal to 2k plus 1 for some k, right? Technically, you might want to say for some integer k. But again, you're not terribly, I mean, this is just technicality, right? As long as you know that k is some integer, right? It's not a rational number, it's not a real number. It can't be something crazy. So then what we get to do is we get to just write out n squared, which is equal to 2k plus 1 squared, which as it turns out is equal to 4k squared plus 4k plus 1, right? So given that fact, oh, I'm not streaming to the Discord. I guess I'll stream to the Discord as well. There we go. Okay. Anyway, getting back to this. So what can we say about this thing? Well, so is n squared odd, right? Is n squared odd? And so what you see here is that there's this extra plus 1 on the end, so that's what you really want. We just have to make sure that each thing here can be factored out by 2. So you might choose to write this as 2 times 2k squared plus 2k plus 1, right? And what this shows is that it's 2 times something plus 1. And so that means it's odd, right? So this might be a fact that you never thought about, but once you see it, you kind of think it makes sense, right? If n is odd, then n squared is odd. You know, and here's the proof of it, right? Because if you have n, you square it, you see that it has the extra plus 1 on it, so it must be odd. Okay, and then, so I'm going to do the reverse direction. So this was the forward direction, right? This was this part. So this is the end of this part here. And so let's look at the other direction. So if n squared is odd, then n is odd. So, all right, I think I want more space. If n squared is odd, then n is odd. Now, actually what I'm going to do here, because I think if I do it, regardless of what I do, I think it's going to end up being this anyway. I'm not going to prove this. Not going to do it. Wouldn't be prudent. So what I'm going to do instead is I'm going to prove the contrapositive. And so your question might be, well, what is the contrapositive of this statement? Well, if this is the proposition, say, P, and this is the proposition Q, right? N squared is odd and n is odd. Those are the two propositions here. Then the contrapositive of this is not Q implies not P, which means that if n is not odd, then n squared is not odd. So, okay, so here's the question then. How do I show this? Like, what do I do to show this? So the first thing is we want to resolve this little bit of English here, right? When I say not odd, what do I mean, right? And so is it true, and I think we said this yesterday, or last class on Wednesday, that everything is either even or odd because 0 is even, so there's no problem with 0. And all the other things are either even or odd, right? So everything is either even or odd. So there's like evens, there's odds, and there's not anything in this like other category. There's nothing over here, right? So everything is either evens or odds, but there's no category that's like neither even nor odd, right? So if you drew a Venn diagram, it'd actually be more like here's the evens, here's the odds, and then there's just nothing on the outside, and there's no intersection either. So the good news is we can just replace this with n is even, implies, or if n is even, then, so I guess I actually should put an if here. If n is even, then n squared is even. So in the previous part, we proved that if n is odd, that n squared is odd. And here we're going to prove that if n is even, then n squared is even. And as it turns out, because the contrapositive is equivalent to the original statement, it's the same thing as showing that if n squared is odd, then n is odd. So, okay, let's do this then. So if n is even, then n squared is even, so n is equal to 2k here. And so n squared, on the other hand, is equal to 4k squared. And so the argument needs to be that this needs to be even. So all we really have to do here is just factor out a 2 and just say 2k squared. Now, of course, you might be able to tell yourself, well, I know that 4 is, a bunch of 2's. So I don't even need to do this step, and that might be fine. I mean, I'm not going to be very sticklerish about that. I'm just showing you what it is when you boil it down into the definition. So it's fine. All right, and at this point, the whole proof is done, because for the first direction, we showed that if n is odd, then n squared is odd, and then we showed the contrapositive of the reverse direction, so if n is even, then n squared is even. And so what we've done here is we've shown both directions, and so we're done. So that should be way more on divisibility, or not divisibility, on even versus odd than you ever thought you'd get. Yeah. Okay, so I'm going to move on, I guess, unless there's any questions. So I think, and of course this fills me with fear because of last semester, this is definitely the most confusing symbol all semester. And I promise you that, like, last semester people really hated this thing. And I'm going to try to make it slightly, well, I'm not going to try to make it better, I'm just going to try to teach it again and maybe it'll be just as bad. So, if you draw a vertical line, what we mean by that is A divides B. So, yeah, I think that's the reason why everybody is very confused by it. But actually, if you realize, neither way is really backwards because it's a vertical line, right? So, yeah, so if A divides B, then what does it mean? So this symbol means that if A divides B, come on, right, B, then what does it mean? It actually means that B is equal to A times some number x, right? So you could even say, for instance, like, that there exists some x in, say, maybe the integers, so that B is equal to AX. The other way to say it is that b divided by a is in the integers. So it means that b divided by a divides evenly, right? And so, yeah, so let me do a few examples here. So for instance, 3 divides 6. Yes. 17 divides 34. Because 34 is 17 times 2. 3 divides 81, right? Because 81 is equal to 3 to the 4th power. So 3 to the 4th power, so 81, 3 will divide that. I don't know, 15 divides, what's a good example? 75, I guess. Yep, that's true. What else divides? Things like x will divide x squared, so that's true, because x squared is equal to x times x. X will divide, say, 15x, right? That's pretty obvious because x already divides x. Yeah, so here's just a bunch of examples. So I think the reason why people hate this symbol is exactly that people think it's backwards. And maybe it is backwards, I don't know. Unfortunately, it's the way that it was defined, not by me, and not by this textbook. This is actually a fairly standard symbol, and more in number theory. You'll see it if you do a lot of number theory. So number theory is really where you see it. But the book does use it, and unfortunately, yeah, you just have to kind of get used to it. Anyway, so I want to prove this theorem 1.5. The reason why I want to prove it is not because it's complex, but mainly because I want to do more examples with the divisibility bar. So basically what I want to show is that if A divides B and B divides C, then A divides C. And I want to show you how you can kind of, so if this is my claim, then my proof here is going to be something on the order of this. So I'm going to use the fact that if A divides B, then B is equal to, say, AX, right? So, and this is because I guess the other way to think about it is like, if you pretend that this thing tilts back just a little bit, you could always be like, oh yeah, A, kind of like that, but I don't know. I think most people tend to think that if you write something like this, then it should be this, which is wrong. So, okay. And then C is going to be equal to, oh, yes, right. And then because, oh God, I shouldn't write that. Because B divides C. Yeah, exactly. So here what I'm going to say is that B is equal to A times X, C is equal to B times Y. And so you see why I had to pick different letters for these two, right? Because I don't want to use BX again because it could be a different value of X, right? So this is a different number, right? C is equal to B times something, but it's not the same something that makes B equal to A times X, right? So that's why I name it differently. And so here what we're going to do is then we're going to say, well, now we need this fact to be true. So what we're going to do is we're going to say, well, C is equal to B times Y, but then B was equal to A times X. And so if we kind of, I don't know that you have to do this necessarily, but if it'll make it clearer, I think this is kind of more useful. What you do is you kind of group the rest of the crap together, and then you see, oh, C is equal to A times something. I don't care what this something is. Yes, it's equal to XY. Yes, those are the numbers we defined. But really, the important thing is C is equal to A times something. So if C is equal to A times something, you can say, therefore, A divides C. like that. Okay? Cool. I know I didn't ask if there were any questions. Are there any questions about that before I move on? Or do you guys just not like the symbol? Because I know that most of you are sitting there going, ugh, this symbol is terrible and it's confusing me. Okay. Okay, cool. Yeah, I mean, it just takes a while to get used to. Okay, so let's play around with it some more. So for all ABC integers, my claim is that if A divides B, oh wait, crap, wow, somebody is stupid because I'm copying the wrong thing, then yes, if A divides B and A divides C, so this is not A divides B and B divides C like the last time, this is A divides B and A divides C, then A divides, I think it doesn't really matter, 2B minus 3C, like this. So, okay, what do we want to do here, right? What we want to do is we want to, so here's our claim. And so the proof is going to be, well, what is the proof going to be? So the proof is always, you start with whatever you assume. So we're assuming that A divides B and A divides C. So what we're going to do is use those two facts. So we're going to say B is equal to AX, and C is going to be equal to AY, like that. Okay, so this is just given by our assumptions, right? This is, so by definition. So then what we get to do here is we get to write 2B minus 3C as a combination here. So we can write it as 2AX minus 3C's, so it's going to be AY's, right? And so then what's the next step here? So what do we do next? What to do next? So the point about what to do next is that in order to prove that A divides this whole thing, all we have to do now is factor the A out. So we factor the A out, and now we have 2x minus 3y, which we don't really understand what this number is more than it's just some random thing. What we do understand is that at least, for homework, can we refer to things by saying it's been previously proved that? Yeah, I mean, if you use a result from class, then you can say something like, that. Like, you know, in class we show that this fact is true. The only exception to that is if I ask you to show something that's so basic that it's clearly just directly from the definition, and what we proved in class was like a sledgehammer, then avoid using that definition or using that theorem in class. But yeah, basically, yeah, you can use results. If I don't tell you not to, you can basically just use results. So yeah, okay, so here, what this is saying is that 2b minus 3c is equal to a times something, where SMTH means something. And so what we've done here is we've proved that a divides 2b minus 3c. And that's it, right? I mean, really the setup is just as long as the proof. I mean, the proof is really this goes to this goes to this. And that's it. So there's not much here. It's just, I think it's a good example because, yeah, it's a good example. So this is a problem from the textbook that's listed, I think, under the hard problems, but I don't understand exactly what makes it hard. It says if AB divides C, then A divides C and B divides C. Right, so if this is our claim, then what do, right? So if AB divides C, then what we know is that C is equal to ABX, right, by definition. That's what this symbol tells us. And so does this show that A divides C? Well, yes, because C is equal to ABX. And does it so this shows that A divides C. And does this show that B divides C? Yes, because C is equal to BAX. So B divides C. I think that this would have been a reasonable homework problem if I hadn't just gone over it right here. I think this would have been a fine problem. I don't know. I just I think it's fine. I'm not convinced that it's, unless the H symbol is something I don't understand. Anyway. Okay. Any questions about this type of thing? I think this is just about the same as the other problem. And so let me just say that there's a ton of results, right? About divisibility. So we're not getting into all the different results. There's so many different results about divisibility, it's really impossible to even try to attack them all. Okay. So let's see here. Yeah, maybe I'll leave this one for homework, because I think it's about equivalent, and this one we just did. So I'm going to move on from this. Okay, so I assume that most of you have heard of what a prime is, but I just wanted to write down a definition. So a natural number n is prime when for any 1 less than k less than n. So basically, you could even say for any could just mean for all k such that 1 is less than k is less than n, then and this symbol means k does not divide n, right? So this is does not divide. All right. And so that's what a prime is. Prime is something that's not divisible by anything other than 1 in itself, which is exactly what this is saying. So remember that this is not equal to, right? Because 1 divides everything, right? For all x, 1 divides x, and for all x, x divides x, right? So in those cases, 1 is going to divide every number, and x is going to divide every number when that number is x, right? X is going to divide itself, so that's why we don't really care about those two n limits. It's just nothing in between divides it, so that defines a prime. If a number is not a prime, then we call it a composite number. So a composite number basically, so when we say something is composite, so we would say that n is composite when there exists two numbers, say x and y, such that x and y are both not equal to 1, right? So if either of them is equal to 1, then it's no good. But if both of them are not equal to 1 and n is equal to xy, then that's fine. The other problem is, so there are some slight issues with this definition, I guess. I'm just thinking about it more carefully now. So for instance, if this is inside of the natural numbers, that's okay. But if this is doing integers, then we could say, oh, 3 is composite because it's equal to -1 times -3, right? Where neither one is exactly the number 1. So what we'd have to say in the integer case is that there exists some, x and y, such that they're not equal to either plus or minus 1, right? We'd have to add the plus or minus 1 condition in there for integers. So that's something to understand, because in this case we don't want to say that 3 is composite, right? Because just because you can make -1 times -3 equal to 3 versus 3 is equal to 1 times 3, you don't want this to be, you don't want it to be prime here. This is kind of saying, oh, hey, I might be prime, and this is saying, wait a second, you're composite. So that's a problem. This is also the reason why. Is this the reason why? Does this definition so? I guess this definition actually allows. I guess what we need to do is say n has to be not equal to 1. That needs to be added to this definition to just assert that 1 is not prime. So basically, I guess we wouldn't really call 1 prime or composite. 1 is like the neither thing, right? But if a number is bigger than 1, then it's either prime or composite. So if n is bigger than 1, then it's either prime or composite. But if n is equal to 1, then it's just 1. There were, historically, I think in the 1800s, at least historically, 1 was actually called prime. And the reason that they did this was because it fits this definition. And so they would just add it into this list. So in the 1800s, they would just throw this number into the list and call it prime. But we don't do that anymore. And I'll show you the reason why I think we generally don't do that in just a few slides. So we won't, or actually one slide. Okay, so here are some primes. So like 2, 3, 5, 7. 9 is not a prime, right? 9 is not a prime because it's equal to 3 times 3. Something like 15 is not prime because it's equal to 3 times 5. Something like, I think the one that's always a little bit tricky is 51. It's equal to 3 times 17. Something like 16 is equal to 4 times 4. It's also equal to 2 times 8. Or 8 times 2. So as it turns out, that it doesn't, just being composite doesn't mean you exactly have one pair of x, y, such that the number n is equal to x times y. It means that there's at least one pair. So any of these are possible values of x and y. It's just, and it doesn't matter because in this case, neither one of them are plus or minus 1. So all three of these say that it's composite. Now, just saying that this is equal to 1 times 16, right, this does not say that it's prime, right? Just because a number is equal to 1 times itself, that doesn't make it prime. The fact is that the only way to make it prime is that every possible way to write the number has to be just 1 times itself. That's the point, is that it has to be all the ways, but there's these other ways, or so this is the other ways. Okay, cool. Let's look at the fundamental theorem of arithmetic. So, actually, this is in the book. They don't call it the fundamental theorem of arithmetic. They just call it like unique factorization of any integer number or any natural number. So, given a natural number n, maybe I'll restrict it so that n is bigger than 1. There's a unique factorization of the form p1 to the alpha 1, p2 to the alpha 2, ... pn to the alpha n, where pi's are primes. So what do I mean by this, right? So let's just look at the example that I have written right here. So for instance, 24 is equal to 8 times 3, which is true. But 8 times 3 is really equal to 2 cubed times 3 to the 1. Right, so if you wrote something down like 75 is equal to, I think it's what, 5 times 15? So 5 times 15 is okay, but 15 is not prime, so this is equal to 5 times 3 times 5, which is equal to 3 to the 1 times 5 squared. What's another example? So I guess the example 7 is just equal to 7 to the 1, and this is what you get when you have a prime. What's another example? So 81 is equal to 9 times 9. But this is not the prime factorization because 9 isn't prime. So in order to complete the prime factorization, you have to write this out as 3 times 3 times 3 times 3, which then gives you 3 to the 4th power, which is the one that you want. So this is its prime factorization. This is just true, but this is actually the prime factorization. So, okay. So basically that's all that's saying, right? Is that any number can be pulled apart into a bunch of different primes to a bunch of different powers. I'm not always saying, so it is not always true that P1 is going to be equal to the first prime 2, P2 is going to be equal to 3. So it's not always true, right? Right, so that's why we just use P1, P2, Pn, because they can be different primes. They can be a whole bunch of different primes. Normally, you'll write them in ascending order. So normally you'll write P1 is less than P2, is less than P3, is less than ... is less than Pn. And the reason why you're going to do that is just so that, well, there's two reasons. One is so that it's a unique factorization and then the number, permutations of this are not considered, but the other reason is just for the prettiness of it. So, okay. So that is the fundamental theorem of arithmetic, is that everything can be factors, a unique product of primes. So I think what I mean by that is to say that, and what I mean when I say unique is that if I give you two prime factorizations, or if I give you two numbers, or two ways to factor something, then actually they, as it turns out, they have to be the same way. So if I say that one number, so if you have a number that's equal to like P1 times P2 times P3, and you have, here's another prime factorization, n is equal to P1 times, say, P4, so some different prime, this is not possible. And it would look really weird, too, because if you said something like n is equal to, say, 2 times 3 times 5, right? And then also n is equal to, say, 2 times 7, immediately you're going to be like, well, that particular thing isn't true. But that should actually never be true, because if here you have a factor of 7 in you, and here they have a factor of 3 and 5, right? It's not possible that n can be both, right? Because here n doesn't have a factor of 7, here n doesn't have a factor of 3 and 5, so here this is some kind of nonsense, right? And it looks more possible when you write it out without specific numbers, but as soon as you pick some primes and write something like this out, you're like, wait a second, this can't be right, this cannot be possible. Okay, so let's move on, now that I've said all that, to the GCD. So the GCD is the greatest common divisor of two numbers. So what is it? So what does it mean to be the GCD? What it means is that if you have two numbers a and b, the GCD is the biggest number such that g divides a and g divides b. So basically you need that a divided by g is an integer, and also b divided by g is an integer. But we want to make this as big as possible. So g gets to be maximum of something, right? So, okay. Yeah, so here, for instance, 16 and 80, okay. We'll define the relatively prime business in just a second. Let's just go through these examples first. So, one way to determine if something is the GCD of two numbers is to write out their prime factorization. So let me show you an example here. So here, 12 is equal to 3 times 4, which is not the prime factorization, and 20 is equal to 5 times 4, which is also not the prime factorization, right? Because 4 is not prime. 3 and 5 are prime, but 4 isn't prime. So in order to do the prime factorization of these numbers, you need to write this out as 2 squared times 3, and you need to write this out as 2 squared times 5. So the trick here to find the GCD of two numbers is that what you get to do is you get to look at these things and you say, ah, I have a prime here that's shared. So the GCD of this is going to include a 2 to the something. And you notice that they're both actually 2 squared, so it's not going to matter in this case, but whatever. So the point is here, we know that there's a factor of 2 squared in here, there's a factor of 2 squared in here, so it's going to be 2 squared. And then here you say, well, there's a factor of 3, but there's no factor of 3 here, so we can write maybe a 3 to the 0. Here we get 3 to the 1. And so what we're going to take is we're going to take the minimum of the two powers. So this is going to be 3 to the min of 0 and 1 in this case, which is just 0. And then the same thing for 5, right? It's going to be 5 to the 0, or 5 to the 1. And the answer is that if we're taking the GCD, if we took the bigger number, right, and we said, okay, well, 12 divided by 5 is what, right? And then 20 divided by 5. 20 divided by 4, which is okay. 12 divided by 5 is what, 2.4, which is, not okay. And so that's the point here, is that we can't take a number that doesn't have a factor in both terms. So, or that isn't a factor of both terms is probably the better way to say it. So, okay, let's think about it this way. So what about 25 and 30? So 25 is 5 squared. So the GCD of 25 is this. The GCD of 30, so 30 is equal to 2 times 3 times 5. And each one of these is to the first power. So in order to get the GCD of this number, we're going to look at it and say, well, what's the minimum power here of 2's? It's going to be 2 to the 0 because there's no 0 over here. Or I'm sorry, there's no 2 over here. It's going to be 3 to the 0 because there's no 3 over here. And it's going to be 5 to the 1 because there's a 5 squared here and there's a 5 to the 1 here. But we take the minimum. And so if you think about it, this is as good as we can do, because if we took 2, then 25 divided by 2 doesn't evenly divide. 25 divided by 3 doesn't evenly divide. 25 divided by 25 it works, but 30 divided by 25 is what? It's like 1.2, so not an integer. So that's why the best we can do is just 5. Yeah, so similarly here, oh wait, that's a typo. 1681, that's 1. There we go. So let me go through that one. Let's skip this. Well, actually, let's do this one. So the GCD of 72, so what is 72? So 72, to my knowledge, is 6 times 12. But that's not the prime factorization of it. 18 is equal to 6 times 3, I guess, which is also not the prime factorization. But at least this is prime. So then if we look at the prime factorization of this, we'll get GCD of 6, which is 2 times 3, times 3. And then here, 12 is equal to 2 squared times 3. So in this case, we're going to have 2 cubed times 3 squared, like that. And then here, we're going to get, this is 2 times 3 again, so 2 times 3. So then we're going to get 2 times 3 squared. And so if you remember, what we have to do is we have to take the minimum power in both terms. So here we have a 2 to the 1, or we have a 2 to the 3, so we take 2 to the 1. And then here we take 3 squared, or we take 3 squared. Both of them are the same, so we take 3 squared. And so that's how we compute these things. And of course, 2 times 9 is equal to 18, so it just becomes 18 again. So it's always possible. The reason why this is the case is because 72 divided by 18 is an integer, right? So what is 72 divided by 18? Is that 4? Yeah. And I guess the last one to talk about is the 16 and 81 business. So we know that 16 is 2 to the 4th, and we know that 81 is 3 to the 4th. And so if you have the GCD of 2 to the 4th and 3 to the 4th, then you know that neither of them share any primes in common. So if neither of them share any primes in common, then their GCD is 1. Okay. So, yep. And so just to go back to this last definition here, that's why we call two numbers, when two numbers have a GCD of 1, we will call them relatively prime. And the reason why we do that is because they don't share any primes. So A and B have no primes in common in their prime factorization. So that's the way to think about it. And that's why we call them relatively prime, because this B doesn't have any primes from A and A doesn't have any primes from B, so they're relatively prime. Even though they're not actually prime, because they're like, obviously these numbers are very composite. They have, this one's factorable into a, 2 to the 4th, 3 to the 4th, so they're not prime, but they are relatively prime. Okay, so I think that's all I want to say about GCD for now. Okay. So let's just do a little bit of a proof with this thing. So if A divides BC, and the GCD of B and C is equal to 1, and then I guess actually this is also another assumption, right? So this is assume these two things, and then what we want to show is that if A does not divide B, then A divides C, right? So here's the question. What do we know here? And so there's a lot of assumptions. So the three things that we know are that A divides BC, the GCD of B and C is 1, and we know that A does not divide B. The only thing we want to show left is that A divides C. So, okay, so how do we show this? So what does this mean? Well, that's the first thing that you want to do. Yes, exactly. So you want to say that B times C is equal to A times X, like this, right? And then what we really want to say eventually is we want to kind of get rid of this B part, right? That's what we want to do. And so how do we do it? The answer is, I think we might want to use, we basically want to use the fact that the GCD is 1 here. We want to basically use this fact. So if the GCD is 1, that means that B and C are relatively prime. So if B and C are relatively prime, and I tell you that A doesn't divide B, then what do we know? Then what we know is that, let's write out B and C in terms of their prime factorization. So we're going to write B out as P1 to say that, well, maybe I'll use beta 1 because it's B, P2 to the beta 2, and then Pn to the beta n. And then C is going to be equal to P1 to the, I don't know, let's just call it gamma 1, P2 to the gamma 2, all the way down to Pn to the gamma n. And so as it turns out, what this means here is that, and notice that I'm using the same primes in both lists. So this prime is equal to this prime is equal to this prime is equal to this prime. So if they're relatively prime, what we know about this is that B1 isn't 0 means that gamma 1 is 0, for instance. So whichever one, only one of these cannot be 0 at a given time. So for instance, if I write out like 2 times 3 times 5 times 7, for instance, as some primes, 2, 3, 5, 7, and we write out two numbers that are relatively prime, if I say that this is 2 cubed times, say, 3 to the 0 times 5 squared times 7 to the 0, and this one is 0, 3, 0, 4, then what we know is that these numbers can be relatively prime because this one has some factors of 2, this one doesn't have any factors of 2, this one has some factors of 3, this one doesn't, this one has some factors of 5, this one doesn't, and this one has some factors of 7, But finally, this one doesn't. So therefore, they're relatively prime. And so the GCD of these numbers is 1. Is this actually true? Or am I stupid here? If A divides BC and the GCD of B and C is 1, then if A does not divide B, then A divides C. Is this true? No. No, this is not true. Where did I get this problem? I know I copied this from somewhere, so I must have copied this wrong. I'm looking at this now, and I'm like, well, this is just false. I mean, this is the way to go about it if... yeah, if B and C are relatively prime. So the problem is that A can be anything. So here's the example that I'm thinking of right now. Just B is equal to 3, C is equal to 5. So the GCD of B and C is 1. But, so the counterexample here that I'm thinking of is that if you set A equal to 15 now, we know that A does not divide B, but also A does not divide C, because A is a composition of the two of them. So, yeah, I think what we actually need is this. We will actually want A and B to have GCD 1. But I think that might not fix it either. Well, actually it would. So that would fix it. Yeah, I think I was just yeah. So this is how we have to fix this. So yeah, the GCD of A and B has to be 1. Then, and of course if the GCD of A and B is 1, then we don't need this assumption. We'll just get A divides C. So let's do that problem instead. So for instance here, basically if A divides BC, and the GCD, not of of B and C, but of A and B is equal to 1, then we can say that A divides C. So this is true. So finally we've said something true. And the proof is going to be the same as I attempted to do last time. I think I was thinking this, but I must have just, yeah, that'll fix that. Okay. So this is the true version. So why is this the better version? The reason why this is the better version is if you write, let's just write everything out. So we write out A is P1 to the alpha 1, Pn to the alpha n. B is going to be equal to P1 to the beta 1. Same thing as before. We're going to use unique factorization all the way down to Pn to the beta n. And C is going to be equal to P1 to the gamma 1 ... P1, or Pn to the gamma n. So the thing that I want to talk about here in terms of is that what is multiplication? So BC, right, when we have this long factored out form here, when we have this, then what we know is that BC is going to be equal to P1 to the beta 1 plus gamma 1, right? Because when you have two numbers multiplied together, so if we multiply all these together, then we see that their powers add, right? So that's the point that I want to make here. So BC is going to be equal to P1 to the beta plus gamma 1 times P2 to the beta 2 plus gamma 2, P3, right, to the beta 3 plus gamma 3, all the way down to Pn to the beta n plus gamma n. Okay. Yes. And so if we're saying that the GCD of A and B is 1, then what that says is that only one of alpha I and beta I can be non-zero. So if alpha I is non-zero, then beta I has to be 0. If beta I is 0, then alpha I has to be 0. Whatever. So they have to pair off, and so for instance, if you're looking at the power of 7, so if one of them is 7 cubed, then you know the other one has to have a 7 to the 0 in it. If one of them has, say, 13 to the 0, then the other one can also be 13 to the 0. Or it can be, say, like 13 squared, or it can be 13 to the, I don't know, 125 power. It doesn't matter as long as if this one is 13 to the 0, then you're allowed to have either 0 or non-zero. But if one of them is non-zero, then the other one has to be 0. So basically, the other way to think about it is you can always write that alpha I times beta I is equal to 0 for all I. That's one way to say it. That's true. So if alpha I times beta I is equal to 0, then can we conclude that A divides C? And the answer is yes, because we notice that if alpha I beta I is always 0, then what that means is that for any of the alpha i's that are non-zero, we need that alpha I has to be less than or equal to beta I plus gamma I. And the reason why this is true is because if a number is going to divide, right, if a number, so I say like 2 to the 4th divides, say, 2 to the 7th, then what we need is 4 to be less than 7, right? That's the equivalent statement when you have a single prime. And so, for instance, here, if I said 2 to the 8th divides 2 to the squared, this would be saying that 64 divides 4, which is not true, right? Not true. So that would be that 8 is less than 2, which is false. So if we know that alpha I is less than beta I plus gamma I, and we know that alpha I times beta I is always 0, so that means that if alpha I is greater than 0, then beta I is 0, then this means that alpha I is always less than or equal to gamma I. And so that's what does it for us. This is the identity that proves it. Because as soon as we get down to this identity, then we know that whatever number is in alpha 1, it's less than gamma 1, alpha 2 is less than gamma 2, alpha 3 is less than gamma 3. It could also be 0, right? But then 0, if 0 is equal to alpha I, then it's definitely less than the gamma I. So it's either 0 or it's a number. If it's a number, then beta I is equal to 0. Yeah, maybe I'll write that out. So basically, if alpha I is equal to 0, then 0 is less than equal to beta I plus gamma I. Because, oops. But then if alpha I is not equal to 0, then alpha I is less than or equal to 0 plus gamma I, because if alpha I is not equal to 0, then beta I has to be equal to 0. And so in this case where all the alpha i's are not 0, alpha I has to be less than or equal to gamma I. Therefore, P1 to the alpha 1 to P1 to the alpha n, or Pn to the alpha l, has to divide P1 to the gamma 1, P1 to the gamma n, which is C, and this is A. Yeah, so I'm assuming that this one confused people. Let me think if there's a better way to say this. I mean, probably, since I definitely confused everybody. Basically, I think the way to think about all this prime factorization stuff is that sometimes what you need to do is you need to break up. So let's just do this example, except where there's only 2 primes. So let's say that A is equal to, say, 2 to the x times 3 to the y. B is equal to 2 to the z times 3 to the k. And C is equal to 2 to the r times 3 to the s. And so what I'm saying is that we're going to assume that A divides BC, right? So if A divides BC, then what we know is that 2 to the x times 3 to the y divides 2 to the z plus r in this case, 3 to the k plus s, like that. Because when you multiply 2 numbers, their primes get added up, or their powers get added up, I should say. So this is all, I mean, this is essentially the identical argument. And then what I'm going to say is that the GCD of A and B is equal to 1. So what that means is that if we have any powers of 2, then B can't. So for instance, if x is not equal to 0, then z is equal to 0. And also if z is not equal to 0, then x is equal to 0. That's what it means to have the GCD be 1. So in this case, if one of them is 0, then the other one can't be, or I'm sorry, if one of them isn't 0, then the other one has to be 0. And it's the same thing for the powers of 3. So if say y is not equal to 0, right? If y is not equal to 0, what that means is that there's a power of 3 inside of A. And what that means is that since the GCD is 1, then there cannot be any powers of 3 inside of B. So if y is not equal to 0, then k is equal to 0. And also if k is not equal to 0, then y is equal to 0. So that's what this means. And so all I'm saying here is that basically A and B don't share any of these powers. So basically, like, let's just do an even more concrete example. So let's say A is equal to 16. And let's say that B is equal to 27. Right? And then C would be equal to, I don't know, C can be equal to basically anything. What is like 9 times, let's just make it, well actually let's not even write it out like that. Let's just say it's 9 times 16 or something, or 9 times 32 or something like that. Whatever 9 times 32 is, I guess that's 320 minus 32, so what, 288, I guess. Yeah. So, okay. Cool. So then here, all I'm saying is that if A and B don't share any factors in common, then C has to have all the pieces of A inside of it. So basically, A in this case is just a bunch of powers of 2. And so B can't have any powers of 2, but A divides BC, so C has to have all the powers of 2. That's really what we're saying here, is like, I guess actually, yeah, so A and B share no factors, share no powers of 2. So that's what I'm saying, A and B share no powers of 2. So all the powers of 2 in A must be in C. And the reason for this is because this fact. So because of this fact, we know this. So that's what I'm saying about all this. And so the only extension, so the only difference between what I've just said here and what I'm saying here is that I'm not naming what the primes are. I'm just saying there's n primes. I don't know what they are. They can be anything. They can be 2, they can be 3, they can be 27, they can be 2017. They can be anything. I guess they can't be 27 if I said that. They can't be 27 because that's not a prime. But they could be 2, 3, 5, 7, 13, 89, whatever. So that's the point. And so actually this argument here is basically saying anything that is in A cannot be in B, so it has to be in C. That's all I'm really saying. Okay. I'm going to move on because I probably confused everybody quite a bit with this. And, yeah, okay. So, I guess if you hated that one, then this one's worse. So hopefully I'll take... So the least common multiple of A and B is the least number m such that A divides m and B divides m. So if you remember what GCD means, it's the greatest number such that G divides A and G divides B. So basically, yeah. So this is what happens when you flip the definition. So what is an LCM of two numbers? So let's do some experiments with LCM. So what is the LCM of, say, 4 and 25? The least common multiple. So it's something such that, 4 has to divide this and 25 has to divide this. So I'm going to say that this is 100. And the reason why that's true is because 100 divided by 4 is 25, and 100 divided by 25 is 4. Let's look at something else. What is the least common multiple of, say, 18 and, 27? Let's do 18 and 27. So this is where we look at the prime factorization. So the prime factorization of 18 is 2 times 3 squared. The prime factorization of 27 is equal to 3 cubed. And so the least common multiple, so the multiple is going to be something that, and remember, 27 has to divide our multiple, and 18 has to divide our multiple. But the good news is that we get a little head start, because if we start the number at 18, if we just look at 18, it's going to have this 2 in it, and it's also going to have this 9 in it. So the only thing we have to do is actually multiply by an additional 3. And the reason why is because you actually just have to look at these two prime factorizations and you take the maximum of the two numbers. So here we have a 2 to the 0 power. You have a 2 to the 0 power, here you have a 2 to the 1 power. So the LCM is going to be a 2 to the max power. And in this case, the max is going to be 1. And then you get a 3 to the max power. And here, the two powers of 3 are 2 and 3. And so it's basically the maximum of 2 and 3 is 3, and the max of 0 and 1 is 1. And so what we're going to get is a 2 to the 1 times 3 cubed, which means that this is going to be 27 times 2, which I guess is 54. And so the point here is that 18 is equal to, 54 divided by 18 is 3, and 54 divided by 27 is 2. And as it turns out, that is the least common multiple of 18 and 27. So let's look at this other part here. So these things are just true regardless, but I'm using them in this proof, so okay, I guess Doggo wasn't interested in being on camera. Anyway, So what should I say here? If we use unique factorization to produce these two factorizations, so p1 to the alpha 1, p2 to the alpha 2, pn to the alpha n, that's A. B is going to be p1 to the beta 1, p2 to the beta 2, pn to the beta n. Then, as I've said before, A times B is equal to p1 to the alpha 1 plus beta 1, p2 to the alpha 2 plus beta 2, pn to the alpha n plus beta n. So you just see that basically what happens is when you multiply them, you just add these two things together, right? That's what multiplication does to powers. So yeah, if you have like 2 to the 3, this is basically the same thing as saying 2 to the 3 times 2 to the 4 is equal to 2 to the 7th power. That's all it's really saying. And then you just do that for 3, do that for 5, do that for 7, do that for 13, do that for, I guess, 11 if I skipped it, whatever. So the other thing that I'm saying here is that the GCD of A and B, the GCD of any two numbers, is P1 to the minimum of the two alpha 1, beta 1 powers, P2 to the minimum of the powers, Pn to the minimum of the powers. The LCM, on the other hand, is P1 to the maximum of the powers, P2 to the maximum of the powers, Pn to the maximum of the powers. So I want to argue that the LCM of A and B is equal to AB divided by GCD of AB. Right? So this is a fact. It's also, all the other facts are true. I think what you can even do is you can say that the GCD times the LCM, this is probably the way that we want to prove it, is equal to the original number, AB, or the original product. It's equal to A times B. And so why is that true, right? So it's true because if you look at any given prime, right, the minimum of the two numbers is going to be one of them. The maximum is going to be one of them. So let's think of all the different cases that can happen, right? What are all the different cases? So you have the cases where alpha 1 is less than beta 1, strictly. I guess alpha I is less than beta I. In that case, the maximum is beta I and the minimum is alpha I. So what we get here is that this will give us the minimum, so the GCD is going to produce an alpha I. The LCM is going to produce a beta I. So we're going to get an alpha I plus a beta I in the PI power. Let's write this somewhere else. So yeah, in the PI power, and we have the GCD of A and B times the LCM of A and B. And I want to say that that's equal to AB. So if we're just looking at the PI power, and I tell you that the power, so I tell you that alpha I is less than beta I, then what we know is that this is going to give us a PI to the minimum, which is alpha I. This is going to give a PI to the maximum, which is PI to the beta I. And so that's equal, at least in the PI term, to PI to the alpha I. Whoops. Wish this thing would write. It's really screwing up. Wow. I'm getting like 1/10 of it is writing. Okay. All right. And now, similarly, if beta I is less than alpha I, then what we're going to get here is that the GCD is going to give us PI to the beta I. This is going to give us PI to the alpha I for the for the LCM. And finally, we're going to get, this is, at least in terms of the ith prime, we're going to get PI to the alpha I plus beta I. Again. So this times this is equal to this. So yes, yes. The last case is where they're equal, where beta I is equal to alpha I. In that case, it really doesn't matter because the minimum is equal to the maximum, right? The minimum is equal to the maximum here. And so if the minimum is equal to the maximum, then what you can say is that it doesn't matter. So we'll just say that this one is PI to the alpha I, and the other one is PI to the beta I. Now, of course, they're actually technically both to the alpha I. They're also technically both to the beta I because they're equal. But it doesn't really matter. Let's just call one of them alpha I and one of them beta I, and then you get to say, oh, this is equal to the pi to the alpha I plus beta I. God, I really wish this was right. There we go. And so that's the point here, is that in terms of each power, if you basically restrict both numbers to just the pi power, and you look at what the powers are in terms of each one of them, then what you'll see is that in each case, either you're going to get the alpha in the GCD or you're going to get the beta in the GCD. And if you get which one in which thing, then you're going to get the other one in the LCM and then the other one in the LCM. So, yeah, that's basically the proof of this fact. So this fact says that the least common multiple is equal to the two numbers multiplied together divided by the GCD. And so that is true. All right. So I suggest that maybe I'll actually just write up the rest of this proof using LaTeX, and then we'll actually look at it. But let me see what the next slide is using modulus, and then I think. Okay. So we have a few slides before we get to induction. All right, I guess we'll take a break, take a 15-minute break. So we'll be back at, so it's 2:32 right now. We'll be back at 2:47. I'll start at 2:47. All right, let's do it. Okay, good. I unmuted myself instead of doing anything stupid. Okay. All right, so I am back at least. I'll give everybody a minute or two to come back. I think someone asked if I would go over number 7 on the homework. So I will do that. Let me readjust all my windows. So, okay. Let's see. I think this is the updated version. Let me just copy it onto a new slide. Okay. R or not S. Oh Lord. T or R. T implies Q. And not Q and P. E. Okay. So, yeah, so what's your question about number 7? Oh, okay. Okay. So you had to prove R. Prove W and T. Am I looking at the right thing? Because I vaguely remember that. Is that the quiz problem? Or where is that from? Oh, is it S and T now or something? Prove S or T. So I see that number 8 is, oh my God, please write. Q and not S implies T. Yeah, P or Q. Not W and P implies W. So, presumably, what you would do is you would look at not W first, and you would say, well, P implies W, and not W give me not P. Yeah, and then, so that's, I think I pulled a tricky bit here. So this is tricky. I'll explain what I'm doing in just a second. What the thing that you have to do, so all that part is probably the easy part where you get this and then you use this to eliminate and get Q, and then you have Q and not S implies T, but Q is going to be true then. And so what we're going to do is we're going to say that what is Q and not S implies T, and the answer is that this is not Q, right, because of the equivalence, and not S implies, or T. So if we use De Morgan's law, what we're going to get is not Q, or S, or T. And so what we can actually do is, we know that Q is true. So not Q is false. So actually what we can do is do another elimination. So this is just elimination. And so if we eliminate, then we're just going to get S or T. So yeah, we had to do a little bit of logic algebra to convert Q and not S implies T into not Q and not S implies T into not Q or S or T. Yes. And so then you use the rest of this stuff to prove, basically, you prove that Q is true, and then you just eliminate. Are those 7 and 8 on the updated homework? That is a good question. I would imagine that they are, because, yeah, if they look different, then that scares me, because I'm not sure. This is what I have as homework 2, number 7 and 8. This is what the updated PDF should be, I would think. I guess I'll check them on Blackboard once I get back on. Oh, great. What did I... Oh, crap. Well, let me think. Oh, wait a second. Wait a second. This might not be it. Let me check. This might not be it. Let me check. I think there's another version. Is it this? Ah, here it is. Okay, cool. I'm glad that I was able to confuse myself and everyone else. Well, so this part is the same. And oh, maybe I did update. Wow. Must have changed that homework a lot. I think up to 5 is the same, and I think I changed everything here. Yeah, I must have done that. Anyway, okay. Sorry, this is the actual version that I used, I think. Okay. First sentence should be T instead of B. Well, let me write down something and see here if, okay. So let's see. So we want to prove W and T. And our assumptions are that X implies W and V, not Y or X. Y, not T, implies not S and S. Okay, so the first thing you do, I would suppose, is that you look at this thing here and you apply modus tollens. And so what you're going to get is, actually what you're going to get is not T, which means that we know that T is true. Okay. So then the next thing that you do is use elimination here. And so elimination is just going to give us X. And so then here we do X implies W and V, so we're going to get X is true, or and X implies W and V, therefore W and V is true. Well, so it would be W and T if that was the end of the problem. That's not quite the end of the problem. So I think isn't it called specialization, right? Specialization that says that W and V implies V, right? Or I'm sorry, W implies V and V implies W. It also implies V, but we don't care about V. V doesn't exist. V doesn't matter. So now what we have is we have T and we have W. And so now we use conjunction to get W, T. So I think the problem is good the way it is. Yeah, you just have to split this apart because this is an AND statement here. So because this is an AND statement, you basically know that both W is true and V is true. But the point is that V doesn't appear in the rest of the problem. So you kind of just go, oh, well, if W and V is true, then definitely W is true. So now we have W is true. We have T is true. So W and T is true. Yep. Review elimination to get X. Yes. Basically, elimination in general just says that if A or B is true, and I tell you that not B, or not A, it doesn't really matter, not B, for instance, then A. And the reason why is I say, like, if it's either an apple or it's an orange, and then I tell you it's not an apple, then it's going to be an orange, right? So that's what elimination is doing here for us, right? But in this case, this is elimination because it's X or not Y is true. So we say, like, I don't know, and then we say Y is true, and then basically these cancel out and we just get X. So that's how we get that. Oh, no problem. This stuff is not... I would say that in a way some of the stuff is easy, and in a way some of the stuff is very complicated because of all the new symbols and all the kind of confusion that comes from it. So it's definitely not easy, and it does require some playing around. Okay, so what else? Was there a request to talk about number 5? I'll talk about number 5 if you want. So there's 2 ways to do number 5, right? To do 5. 5 basically says that alpha implies beta and gamma is the same thing as alpha. Nope. Yep. Alpha implies beta and alpha implies gamma. So I was thinking about, the way this problem came about is I was thinking about certain things, and I realized that, like, I was thinking about this equivalence in a more concrete way. I was thinking about, I forget where it was. There was this implication statement that I was looking at, or this proof that I was doing, and I was thinking to myself, like, if alpha, then beta and gamma, and then you say, well, if alpha, then beta, and if alpha, then gamma, that should be the same thing, right? So I wrote it down in logical notation. I thought to myself, wow, it's actually a little bit, I'm not sure 100% if these two are identical, and so let's check. And so there's 2 ways to do it. The first way to do it is just to write out a truth table, right? You can write out alpha, beta, and gamma, and just check the truth table of both of these things, right? So if you have, like, true, false, etc., right? And then here you'll get, like, true, false, false, and that one goes with this line here. And then we get true, true, false, false, and then here we'll get, finally we'll get true, false, true, false, true, false, true, false. Okay, cool. And that's the whole truth table. So then beta and gamma. So beta and gamma have to both be true. So let's do beta and gamma. And so here that's going to be true, false, 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 then true, false. True, false, 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 true, false, false, false. And so then alpha implies beta and gamma is going to give us, what is it going to give us? So basically, if alpha is true, then this has to be true. So it's going to give us true here, and then it's going to give us false for the rest of these, because these are all going to be true implies falses. And then here, where alpha is false, then this is just going to give us true for all of these, because these are all the vacuous truths. Could have written it as beta or, I did write it as beta or gamma. Yes. And then here, if we have alpha implies beta, and then we'll have alpha implies gamma, and then we'll have the and statement, which I'll hopefully write as an and this time. Let's see, alpha 2 beta and alpha 2 gamma. I actually think parentheses might be necessary here. Well, okay, they definitely are. I was thinking about that. Yep. So then, okay, alpha 2 beta is going to be true, true, false, false. And now that alpha is false again, we get true, vacuous truth for everything down here. There we go. And then here, alpha to gamma is going to be true here, false here, true here, false here, and then once alpha is false, we get the vacuous truths again. And finally, we have to AND all this together, so we AND this together, we get true, true, true here, true, 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 true here, and here when we AND this together, we're going to get true, false, false, and finally false. And so now we see that this column here matches with this column here. So this is the truth table way to do it. This is my least favorite. I don't like this. Don't like it. Because there's a better way to do it. Well, I shouldn't say better. There's a different way to do it. Here's the different way to do it. We do some set algebra, or logic algebra, so we say this is not alpha or beta and gamma, and then you use the distributive law. And so if you use the distributive law, what you're going to see is that this is going to become not alpha or beta, and not alpha or gamma. And then, of course, everybody says, wait a second. Not alpha or beta is alpha implies beta. And not alpha or gamma is alpha implies gamma. Oh. So we're done. So that was much faster. And I like this one more. This one is my fave. My fave. Anyway, so that's all I want to say about number 5, which is basically everything. Okay, let's go and talk about modulus. So I want to introduce a notation that mathematicians use for modulus, and the reason why I want to introduce that notation is mainly because I introduced it in 201 and everyone hated me. So I want to introduce it here so that maybe you won't hate the next person who says it to you. So basically, when we talk about mod mathematically, we use 18 is equivalent to 3 mod 5, right? Because if you remember mod, right, from 201, 202, whatever, what you know is that, like, if we use the parenthesis, or the, what is it, percent sign, that's what I was thinking, percent sign, 18 mod 5 is equal to 3. Also, 3 mod 5 is equal to 3. So both of those are true. And so why do I only write the mod on one side? The reason why we generally write the mod on one side and not the other side, we could write it on both sides, but what you usually understand is that this 3 equal sign thing usually just means is equivalent. So what we mean by this is that, well, I guess I'll say it this way. 3 mod 5 is not just a number. 3 mod 5 is a set of numbers. So if you look at it here, 3 mod 5 is actually this, whoops, crossed it out. 3 mod 5 is actually this set of numbers here, where, for instance, if you take any of these numbers and mod it by 5, you should get 3. And the reason why is because, for instance, 3 divided by 5, right? 3 divided by 5 is 3 remainder 5. Same thing with 13. 13 divided by 5 is equal to 3 remainder 5. And I'm sorry that I've absolutely butchered that 3, so let me get rid of it. And so, like, negative 7 divided by 5. Well, negative 7 divided by 5 is a little bit wonky, right? But if your remainder has to be positive, then it's going to be minus 2 remainder 3. What? Oh man, I'm so dumb. This is not 3 remainder 5. It's, what was I doing? This is what? 2 remainder 3. This is 0 remainder 3. This is minus 2 remainder 3. Okay, there we go. Sorry, it wasn't 2 remainder 5. I kept looking at 3 mod 5 and writing 3 remainder 5, but that's... 3 remainder 5 doesn't make any sense in the mod 5 system because you would never have a remainder of 5. Okay, anyway, now that I've said that and covered my... yeah. Okay, so I fixed that. All right. So yeah, okay. All right, so basically whenever I use this 3 thing, what I mean is that both 18 and 3 are in the same set of the mod 5. Yes, that's right. When you add 10, then you're going to get a 3, right? But adding 10 means that you have multiplied 5 by 2. So multiplying 5 by 2 means that you got, well, really minus 2 in this case, minus 2 with a remainder of 3. So that's how you get that. Yep. Okay. So what else do I want to say? Let me think for a second. Yeah. All right. And so, for instance, if you want to consider the 1 mod 5 set, right, that's going to be equal to things like minus 9, I think minus 4, 1, 6, 11, and since this thing is having trouble writing. This program is having a little bit of trouble writing right now, so I'm just going to say etc. So anyway, yeah, so basically this is what I mean when I use modulus. So this is like the definition of, for instance, being 4 mod 12, right? It's a set of all x such that x mod 12 is, I guess you could say 4 mod 12, but really it's just, you could just say is equal to the number 4, right? X mod 12 spits out the number 4. Okay, so that's what I really want to say about the notation of mod. And with that, let's see. Okay, that's why I wanted to introduce mod. Because I want to go through this little example here. So for Pythagorean triple, okay, so let's recall what a Pythagorean triple is. So a Pythagorean triple is a set of integers. Really, I'm restricting them to natural numbers, a, b, and c, so that they are the sides of a right triangle. And so if they're the sides of a right triangle, right, so anything that's the sides of a right triangle obeys this Pythagorean theorem, right, so that a squared plus b squared is equal to c squared. Now that's true even if these are not Pythagorean triples, right, even if they're not natural numbers. But if they are natural numbers, then we call them a Pythagorean triple, because it's a triple, it's 3 numbers, such that a squared plus b squared is equal to c squared. Okay, so here's a question for you then. Is it true that either 3 divides a or 3 divides b, and one of the 3 numbers is divisible by 5? And so the answer is yes, because it's a proposition, so I'm going to try to prove it. And I'm going to prove it using mod. So what I'm going to do is I'm going to look at a squared plus b squared is equivalent, right? This is like mod equivalent to c squared mod 3, right? So now what I'm going to do is I'm going to say, well, there's only really 3 possibilities for a and b. Either a can be 0, I wish it would write 0, 1, or 2, and b can be 0, 1, or 2, right? Mod 3, right? Now they can be anything, but when they're mod 3, when we mod everything by 3, the only 3 answers that can ever pop out are 0, 1, and 2 for a and b. So what we want to show is that, and then, okay, so the one fact that I'm going to say before we get into actually talking about all this is, what are the residues mod 3? So let me explain what that means. If we look at the equation x squared is equal to, let's call it r, which will stand for residue, mod 3. So as it turns out, this equation is not always solvable, okay? So what I mean by that is that if you plug in x equals 0, 0 squared is 0, mod 3. Wow, this is really fighting me. 1 squared, on the other hand, is 1, mod 3. But 2 squared, what is that, right? So here's the question. What is 2 squared mod 3? Well, 2 squared is 4. So mod 3, this is actually 1. So that's kind of the point here, is that actually, as it turns out, there is not a number, right? Because every number is either equivalent to 0, 1, or 2 mod 3, so there's no solution to this equation. If I say x squared is equivalent to 2 mod 3, there's no solution of this. No solution. Okay? And so that presents an interesting fact, because what we're going to do, and so now that we know that there's no solution to 2 mod 3, right? We look at this and we say either 3 divides A or 3 divides B. Well, if 3 divides A or 3 divides B, then what that means is that A is equivalent to 0 mod 3, right? That's this. If you think about it, that's the same thing. If I say that A divided by 3 is an even number, well, not an even number, but A divided by 3 is an integer, and I say that B divided by 3 is an integer, then the remainder that you get is going to be 0. So these two things are equivalent to saying that this thing is a number. This thing is an integer, and this thing has a remainder 0. So those are the two equivalent statements. So if they're equivalent, then what we get to say is that what we're going to do here is we're going to say, okay, well, what if they're not, right? So what if A is equal to, say, 1 or 2, and B is 1 or 2? So if A is equal to, say, 1 mod 3, so A is equivalent to 1, and B is equivalent to 1. Then what that means is that A squared plus B squared is 1 plus 1, so it's actually going to be, then what we're going to get is we're going to get 2 mod 3 is equivalent to C squared. And of course there should be a mod 3 here, right? Everything gets a mod 3. So is A equals 0 mod 3 an assumption? Well, so what I'm actually doing is I'm assuming not. So this is a proof by contradiction. So I'm going to assume that neither is true. Right? So if I assume that neither is true, then what that means is that A has to be 1 mod 3 and B has to be 1 mod 3, or A has to be 2 mod 3 and B has to be 2 mod 3, or one of them is 1, one of them is 2. Some combination, but they're not 0 mod 3, right? So these are the only 3 possibilities. Either you can be 0, 1, or 2 mod 3, 0, 1, or 2 mod 3. So if you're 1 and 1, then we see that A squared plus B squared, right? 1 squared plus 1 squared is going to be 1 mod 3 plus 1 mod 3, which is 2 mod 3. But we know that this equation here has no solutions, right? That's the whole point of this business, one that I talked about with the word residues. So when I got to 2 is equivalent to C squared, there's no solution. Same thing if you say A is equivalent to 1 and B is equivalent to 2. Because then what that gets you is that 1 squared plus 2 squared is actually the same thing as, this is 1 squared, this is 1 because of this. This is actually 1 because 2 squared is 4, but 4 is actually the same as 1 mod 3. So this will give us 2 again, which is C squared. So if once we get to the equation 2 is equal to C squared, then we know that there's no solution, so that's not possible. And then finally, the last case, so there's the case where we flip A and B, so A is equal to 2, B is equal to 1, but that's going to work out the same way. The last case here is where we have A is the same, is equivalent to 2, and B is equivalent to 2. And in that case, 2 squared plus 2 squared is the same thing as 1 plus 1, which is the same thing as 2. So 1 plus 1 is the same thing as 2, but the problem with that is that now we have the equation 2 is equal to C squared again. So whatever we try to do, right, as long as both of them are not 0, we see that we're going to get 1 plus 1 in the end, which is going to be 2, and 2 equals C squared has no solutions. So that's the point. So that means, so what happened here? So we showed that here's all the possible cases where we assume that A, is not equal. So basically what we're assuming is A is not 0, and we're also assuming that B is not 0. Wow. It really doesn't want to write these vertical lines. Okay. So, So basically that shows that. Okay. And so I'm going to leave it to you guys to show that one of the three numbers is divisible by 5. It's basically the same process. So what you'll want to do here is you'll want to write out, for instance, like if you have three numbers, right? A squared plus b squared, come on, b squared is equal to c squared. And we have that, so the thing is mod 5. So if you divide everything by 5, then there's 5 possibilities. A can either be, so if we do this mod 5, you can either be 0, 1, 2, 3, or 4, right? And so if, let me just think about this for a second. So what we notice is that if you square these numbers, so let's just square these numbers, right? So that we know what a squared, b squared, c squared, and d squared, or a squared, b squared, and c squared are. So 0 squared is 0, mod 5. 1 squared is 1. 2 squared is 4, so that's okay. What is 3 squared? So 3 squared is equal to 9 as a number. But what happens when we mod by 5? Right? What is 9 mod 5? Right? And so the answer to that is, oh, it's 4. So in this case, we see, okay, 3 squared gives us 9, but 9 is really just 4 mod 5. Same thing with 4. 4 squared is going to give us, or a similar thing with 4, I should say. 4 squared is going to give us 16. And if we mod this by 5, what we're going to get is 1. So the residues, these are called quadratic residues, which means in the mod 5 system, there are only certain things that can come out as squares. So if you square 2, you get 4. If you square 3, you get 4. If you square 4, you get 1. So what that means is that there's no solution. There is no solution to the equation x squared is equivalent to please write. It is very difficult to write. Okay, x squared is equivalent to 2 mod 5, or x squared is equal to 3 mod 5. Well, now it's working a little bit better, a little bit. So, yeah, x. Okay. So if x squared is, there's no solutions to these two equations here. So what that means is that if you ever get, so for instance, if you assume that neither a nor b is equivalent to, so I guess that's what we want to say here. So if a or b is 0 mod 5, right, so let's look back and see what we're trying to prove in the first place. We're trying to prove that one of the three numbers is divisible by 5, right? One of the three. So what that means is if a is equal to 0 mod 5, or b is equal to 0 mod 5, or c is equal to 0 mod 5, then we're done, right? So what I'm going to do is I'm going to assume that a is not 0 mod 5, and I'm going to assume that b is not 0 mod 5, right? Because if either one of those is 0, I'm actually going to leave alone the conclusion that c is not 0 because we're going to try to prove that. But I'm going to assume that a is not 0 and b is not 0. And the reason why I'm going to do that is because now we can look at the possibilities where you basically cross off 0. So it's possible that a could be 1 mod 5, right? It's also possible that b could be 1 mod 5. So if a is 1 mod 5 and b is 1 mod 5, then what happens here? So if a is 1 and b is 1, then a squared plus b squared is 2, right? So a squared plus b squared would be 2. Oh my god. Is 2 mod 5. And so then we know that this is not possible, right? So this is a contradiction. You can't have this case. And the reason why is because there's no solution to 2 mod 5 or 3 mod 5. And so if you do something similar, where in this case you say, but now you realize that it didn't matter if a was 1 or a was 4, right? Because 1 squared is the same as 4 squared. So if they're both either 1 or 4, then this is all the same, right? So if they're both 1 or 4, then that's the same. If a and b are now either 2 or 3, and it doesn't matter which, 2 or 3 mod 5, then what we're going to see is that a squared is equal to 4 and b squared is equal to 4. So 4 plus 4 is 8. Oh, I was just hoping it would write. So 4 plus 4 is equal to 8, which is equivalent to 3 mod 5, right? So this also has no solution, right? So there's no solution here. So what that means is that this is an impossible case. So it's not possible. So it is totally, it is not possible that both of them are just 1 or 4 mod 5. It is not possible that both of them are just 2 or 3 mod 5. So that means that A and B have to be mixed. So like, for instance, let's just say that A has to be, for instance, 1 or 4. And B has to be 2 or 3. And so if A, oh wait, I'm writing under myself, so. So A has to be 1 or 4, and B has to be 2 or 3. So what that means is that when we do A squared plus B squared, what we're going to get is, well, 1 squared and 4 squared are both 1, so we're going to get 1 here, mod 5. And 2 squared and 3 squared are both 4 mod 5. So then this is actually going to be possible because this is actually going to be 5 mod 5, which is 0. But if this is the case, then what this tells us is, so this is possible. So this is not a contradiction. So unlike the previous two, right, where we said, let's say that they're the same if A and B are both 1 and 4, or A and B are both 2 and 3, so they give us either both 1s or both 4s. If they do that, then that's not possible because there's no solution to 2 mod 5 and 3 mod 5, or x squared is 2 mod 5 and x squared is 3 mod 5. But there is a solution, probably, to a squared plus b squared is 0 mod 5, right? It's possible because, as it turns out, 0 mod 5 squared, right, is the same thing as 0. So there is a solution to 0 mod 5. So that's okay. So if a squared plus b squared is 0 mod 5, then it's possible that there's a solution. So if you're telling me that a squared plus b squared is equal to c squared, then what we're actually saying here is that c squared is the same thing as 0 mod 5. So if c squared is 0 mod 5, then what that means is that 5 had to divide c. And that's a part, actually maybe I'll make that a homework question. This last step here, yeah, that's a good homework question. So, okay. Questions about this, comments about this. Does this make sense what I'm doing, kind of dividing things into cases? And saying, you know, if it's 1 mod 5 or 1 mod 3, 2 mod 3, in this case we're doing mod 5. Does it make sense at least that if you start out with 0, 1, 2, 3, and 4, when you square them, there's only these three possibilities, right? Because if you square 0, you get 0. If you square 1, you get 1. If you square 2, you get 4. If you square 3, mod 5, you get 4. If you square 4 mod 5, you get 1 again because of this. All right. I'm going to assume that was completely 100% understood and everybody loved it. So now we're going to do something like this. We're going to prove that 11 we're going to prove that 11 does not divide 4 times n squared plus 1. Okay. So you might think that that's pretty nuts. Well, first you might think, well, that's obvious because 11 doesn't divide 4, right? If you do 4 divided by 11, that is not an integer. Yeah, that's my generic assumption, is that everybody, after watching that, is just at least a little bit lost. You should probably rewatch it and just try to figure out, just try to rewrite it yourself and try to understand where I'm coming from. But we're going to do the same trick again here. It's going to be a little bit more. So let's look at this trick. And so what are we going to do here? So is it obvious that 4 doesn't divide, or 11 doesn't divide 4? I would say, yeah, that's pretty obvious. So really what we're asking is, does 11 ever divide n squared plus 1? And so what I want to say is that it's the same thing to ask. So this question, right, does 11 divide n squared plus 1, is the same thing as saying, is n squared plus 1 equivalent to 0 in the mod 11 system? And so, okay, well, let's see if that's the case, right? N squared plus 1 is 0 mod 11. So you might think to yourself, I really don't know how to approach this problem, but you do know one thing. You know that if you're in the mod 11 system, the possible things are 0, 1, 2, let's see if I can write a longer one, 3, 4, 5, 6, 7, this is fun, 8, can I count? I don't know, 9, and 10. And you might say, well, what about 11? You were counting. Well, I say, well, 11 is the same thing as 0 mod 11, right? So this is 0 mod 11, 12 would be 1 mod 11, 13 is 2 mod 11, 14 is 13 mod 11, etc., etc., etc. So when you take everything mod 11, these are the these are the 11 possibilities that can pop out. Either you get 1, 2, 3, 4, 5, 6, all the way up to 10. 11 is not possible because 11 is the same thing as 0. So really, I guess 11 is possible, but in this case, I'm just writing it as, 0 is the same thing as 11. 12 is the same thing as 1. 16 is the same thing as 5. Yes. Right, yes. So the general... Yeah. So if you want to convert from one base to another base, if you have a number and you want to express it in base b, then what you do is you take n mod b, and that's the digit. That's the first like b-based digit, and then the next. So that's step 1. Step 2 is you do n divided by b, and you round down. So this is like the round down of n divided by b, and then you go back to step 1. So for instance, if you wanted to convert, say, 153 into base 11, right? The first thing you would do is you would mod 153 by 11. And what is that? So 121, I'm just going to cheat and use a calculator. So 153 mod 11, because I don't want to accidentally get it wrong, is 10. So the first step is that this would be 10. And then when you divide 153 by 11, what do we get? So 153 divided by 11 is 13.9. So we round that down and we get 13. So that's the, and then we go back to step 1. So now, of course, this is a little bit like hex. So if we're going to represent 10, the first digit is actually going to be like A, which is 10. And so then the next digit is going to be 13 mod 11, which is 2. And then this divided by that is going to be 1. So when you divide again, you're going to get 1. So apparently, if you express 153 in base 10, it's actually 12a in base 11. So that's the general rule of how to convert things from one base to another base, is you mod by the new base and then you divide. You mod by the new base, you divide. And every time you mod, that gives you the new digit. That gives you the new digit. Okay. So what I want to do here is I want to square everything, right? So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. But that's no good because we're in the mod 11 system. So 16 mod 11 is 5, right? So this is 16 mod 11. Same thing here, 25. Well, okay, it's not the same thing. What I mean is 25 is 5 squared. Mod 11, it's going to be 3. And then here what we get is 6 squared, which is 36. 36 mod 11 is 3, again, because, so the reason why that is because 36, right, is equal to 33 plus 3. So that's why it's 3. So 7 squared is 49. 49, as it turns out, is equal to 44 plus 5. So this 7 squared is 5 mod 11. 8 squared is 64. So 64, really, you could either say this is minus 2 mod 11, or as it turns out, minus 2 mod 11 is the same thing as 9 mod 11. So 8 squared is 64. 64 is going to be 55 plus 9, right? That's 55 plus 9. So that is why it is 9 mod 11. 9 squared is 81. So that means 77 plus 4, right? 77 plus 4. And then the last one to do is 10 squared. 10 squared is equal to 100. And so 100 is 99 plus 1, right? 99 plus 1. So basically what we're doing is we're squaring all these numbers and squaring all these numbers and figuring out what are they mod 11. And so what you see here is an interesting pattern, right? What you see is that, and so there's actually, this all has to do with something called quadratic reciprocity, but you see that here these things kind of repeat like this. Which is a kind of really cool fact in mathematics, that this pattern happens. It happens for any prime. So if you mod by any prime, this pattern will emerge. I'm slightly less confident that it will happen for non-primes. But anyway. Okay, so is this thing... So what was the original problem? The original problem was to show that n squared plus 1 is never equal to 0. So we want to show that this doesn't have any solutions. So how do we do that? What we do is we say, well, anything that you square is either going to be 0, 1, 4, 9, 5, or 3, right? So the only possibilities mod 11 are going to be... The possibilities mod 11 are 0, 1, 3, 4, 5, and 9. Right, so these are the possibilities for n squared. Mod 11. And so if those are the only possibilities, then n squared plus 1 can be any of these possibilities. 1, 2, 4, 5, 6, and finally 10. But the thing that we see here, right, is that none of them are 0, right? None of these possibilities are 0. Which means that n squared plus 1 is never. Please write. Is never 0 mod 11. So if it's never 0 mod 11, that means that 11 cannot divide n squared plus 1. And so the original statement had to do with this 4 times thing, so also this. But the only reason why this is true is because okay. So does everyone at least understand that what I'm doing here is I'm just squaring each one of these numbers and then modding by 11, right? That's what I'm doing. And then basically I'm just asking, when you add 1 to any of these possible residues, these things that pop out when you square a number mod 11, do you get 0 again? Well, you start out with 0, but 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 4 is 5. You just never get 0 is the point. On the other hand, if I were to change this problem very slightly and say, what about n squared plus 2, right? Does 11 divide n squared plus 2 ever? Well, the first thing is there's actually a solution to that, because you know if you plug in 3 squared is 9 plus 2 is 11. So 11 divides 11. So it's actually true. So why is it true? It's true because if you do the plus 2 option, we see that these residues, if you do 9 plus 2 here, that's going to be 0 mod 11. So what are other things that give us, oh god, 0 mod, or 9 mod 11? Ugh. Oh wait, but that's easy because we know that we just have to check for those things that give us either 3 or 8. So I guess, if I'm not wrong, yes. So if n is equal to either 3 or n can be 8, or whatever. Yeah, as long as it's n is either 3 or 8 mod 11, then it will be a solution. So that's the key there. So so basically the n squared plus 1 is a specific example where there's no solutions to the equation. If we change the problem very slightly, there are actually solutions to this thing. It just happens to be that this is the one that doesn't have solutions. Okay. So let's do a little bit of trickery here. So these are kind of, actually, let me see. Yeah. So let's do this. And this might actually be the last thing of the day, though maybe I'll start induction a little bit. So I don't want to, you can read this slide, but don't read this slide right now. Read this slide when I post it later. Basically, I want you to tell me, so for instance, if I say, okay, I want to take a number 5 and raise it to the 724th power, right? And I want you to tell me, I don't want you to tell me what the whole number is. So the number is going to be blah, 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 blah. And then it has one last digit, and that's all I care about. I just care about this last digit. So what is the smallest number that goes in here, right? So in order to calculate this number, right, this digit, what you got to see in general is that, for instance, if you start out with 5 to the 0, that's equal to 1. 5 to the 1 is equal to 5. 5 squared is equal to 25. 5 cubed is equal to 125. 5 to the 4th power is 625. Yeah, that's right. That is precisely correct. So 5 to the 5th power, 5 to the 5th power is, I believe it is 3. 1, 2, 5. And so you notice a pattern here, right? Assuming that we're not in this case of 5 to the 0, which is just 1, then what we see is that 5 to any power, right, gives us the last digit is the same. It's always 5. So I don't care. What is 5 to the 724th? What is the last digit of 5 to the 724th? It's going to be 5. That's right. Now, I want you to note one other fact before we move on, is that what we're really doing here, by looking for the last digit, is taking 5 to the 724th and modding it by 10. Because remember, just like when we were talking about the change of base stuff, how do you change base? You mod by the base and then you divide. So if you want to know that digit, whatever digit is in that place is equal to that number modded by the base. And so the base in this case that we use generally is 10. So if I ask you for the last digit of a certain number, then you take that number and mod it by 10. So let's do another example. Let's take 2 to the power 724. Well, how do we deal with that? So let's look at powers of 2. So 2 to the 0 equals 1. So basically, I'm just asking you, what is 2 to the 724 mod 10? So 2 to the 0 is 1. 0 is not 724, so that's not interesting. But 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. I know I'm shocking you here, but then 2 to the 4th, and now I'm just modding everything by 10, so 2 to the 4th is 16, so really all I care about is this 6. 2 to the 5th, but then what is 2 to the 5th? 2 to the 5th is going to be 32, right? So we see 32, 2 to the 6th is going to be 64, the next one's going to be 128, 256. Then we'll get 512. right? 1024. 2048. And just to cap it all off, 4096, right? 4096. Interesting, right? What we see is that as you go up, once you start at 2 to the 1, basically, we see that you go 1, 2, 3, 4, and then you go 1, 2, 3, 4, you go 1, 2, 3, 4, and then you see that the last digit just repeats and repeats over and over again. So how do you calculate the last digit of 2 to the power 204? Well, what we do is actually, we see that the cycle, it has a cycle of length 4, right? So what I'm going to do now is I'm actually just going to say, what is 724 That's right, 724 mod 4. And so what is 724 mod 4? Well, 724 mod 4, I think, isn't it just 0? Let me check. Let me be 100% certain before I say something absolutely stupid. Yep, it's 0. So, this is 0. All right. So unfortunately, we cannot use the 2 to the 0 one. So this one's crap. And we see why this one's crap, because it doesn't appear again in the cycle. But what else is 0 mod 4, right? 4 is 0 mod 4. This will be 2 to the 8th, right? That's 0 mod 4. This one here, right, 1, 2, 3, 4, this will also be, this is 2 to the, 12th, I guess. So that's 0 mod 4. So yes, that is the point here. That every time we get to a multiple of 4, we know that the last digit is going to be, in this case, 6. Right? Yes, I'm going to agree with myself. I think I'm right. So, yeah. All right, any questions about this before I go on? Hopefully this is a little bit of fun to round out the day. I'm going to call this fun. If I can write the word fun, then it will be fun. All right, so what about, okay, so I'm kind of cheating here, and the reason why I'm cheating is because I started with the example of 5, and now we have the example of 2. But as it turns out, we work in a base of 10. The base 10 means that 10 is equal to 2 times 5. So you should always be slightly nervous whenever somebody kind of gives you an example where the two examples are 2 and 5. You should be like, the base that we live in is usually 10, right? Because we got 10 fingers. Are they trying to cheat me here? Are they trying to trick me into some kind of pattern that doesn't otherwise exist? Well, let's check it with 3, right? Now, we're going to do 3 to the power 724. Because, I'm crazy like that. And we're going to mod this by 10. So I want to know, what is 3 to the 724 mod 10, right? So 3 is no longer 2 or 5, so it's not the base. So you know that if this pattern holds for 3, it's more likely that it'll work for other numbers. And of course, 2, 3, and 5 are all primes, so you might be a little bit nervous about that too, but we're going to ignore that fact for just a second and plow on. So here, 3 to the 0, right? Unfortunately, oh my god, that really butchered itself. Okay, let's try again. 3 to the 0, oh, look at that, so much better, is 1. 3 to the 1 is 3. I'm just going to use double equal instead of triple since it's less writing. 3 squared is 9. Is 9. 3 cubed is 27. So we're going to see that the 27 is the 7 is the thing we care about in this case. And then note that 7 times 3 is 21, or 27 times 3 is 81. But it doesn't really matter because 3 to the 4th power is 81. And so we see 81. Right? Now, okay, so that's the, so now the next power, right? So this is 0, this is where it starts to cycle back, right? And let me show you why it starts to cycle back. Because the next one, the next power is going to be 2 to the 5th, which is 243. I guess the next power is going to be what? So that's 600, 729? Yes. And then what's the next one? 729 times 3 would be, I'm just going to use a calculator to do that. 2187. The next one is 6561. Interesting, right? Here's the pattern again. And then when we multiply this by 3 again, what we're going to see is 19,683. So we're going to see a 3. So the point here is that, and I promise you that this pattern will continue. I can attest to this. It will continue. So if I'm asking you, what is 724 mod 4, or mod 10, then what we do is the same thing as we did before. We see that we have a cycle length of what? 1, 2, 3, 4. So what we're going to do is we're going to take, really the cycle goes from here to here, or it goes from here to here, not both. But whatever. It's a cycle length of 4. So we do 724 mod 4 again. And actually, let's just make it 725 this time to make it interesting, right? So 725 mod 4. Since 724 mod 4 was 0, 725 mod 4 is going to be 1. And so what do we know? What does that mean? Right? What does this 1 mean? The 1 means that if we got a 0, then we would go to the 0 step in the cycle. If it's 1, then we go to this step in the cycle. So we know that 3 to the 725 mod 10, which is really known as the first digit, right? This is the first digit. Is 3. Because you use this 1 and you go to the next step, right? So this is 0, this is if it's 1, this is if the result is mod 2 mod 3, and this is the result is 3 mod 3. We see that if the result is 4 mod 3, or I'm sorry, if the result is 4 mod 4, then it's the same as 0 mod 4, so it's the same. So basically, why did I teach this? Is this useful? I'm going to say not useful, not really useful. Not useful. But it is kind of, it's kind of a teaching tool. It's kind of something that you can use to kind of understand mod a little bit better. It's something that teaches us a few things about how, what should I say? Oh, it also gives us a hint as to a certain set of things called, well, not things, a certain result called Fermat's little theorem. If I can write it. Oh my god. I'm just going to type it. There we go. And of course that should have an E in it. So I'm just going to do this. There we go. Perfect. So, anyway, okay. What else? What else? Well, you know what? I'm going to end the class 7 minutes early today, because that's what I'm going to do. I think this is a good place to stop. Tomorrow we will start on induction. But by tomorrow I mean Wednesday. But yeah. Yeah, there's no reason to go on. I mean, I could talk about it, but I think that we've gotten to a good point. So I think maybe I've almost done a better job teaching a little bit of basic number theory than the first time, but I can't tell because I can't see your faces, and it makes me mad. I don't know how well anyone understood anything, really. So, yeah, I guess what I'll do is I will write up a quiz for that as soon as I get access back to Blackboard, which I know it sounds really dumb, but yeah, for instructors, we have that double authentication thing, and so I can't get into Blackboard unless my cell phone's on. And unfortunately, currently it is in someone else's car, not here. So that's a slight problem. Anyway, okay, I will let you guys go. Have a good rest of your day. Well, trust me, no one understood the first time last semester, so maybe this semester, maybe it's better by degree, even if, yeah. So we're going to get practice using this stuff. You'll see it again. The only reason why I went over all of it is so that you can see it when we do induction proofs using some of the more basic parts of it. But if any of this stuff was interesting to you, then you should definitely take Math 407. All right, I'm letting you go. It's time. It's time now that we all leave. So have a great rest of your day. I will release the exam probably tonight sometime. I'll release the quiz probably tonight sometime, and I'll post these notes tonight sometime when I turn my cell phone back on. So cool. All right. See you guys Wednesday. Good luck. Oh wow, my microphone's still on. Shouldn't have that. Goodbye.